If you've ever worked with particle physics, you've probably seen these three equations I have in front of you. These are the field analogies of equations of motion for the scalar, vector, and spinor fields respectively. Today's video, I want to focus specifically on the first equation, the Klein-Gordon equation, which describes a free scalar field. And I want to talk a little bit about where it comes from and where its associated Lagrangian comes from, because those can often feel like they're pulled out of thin air when they're first presented. As a disclaimer, I'm working not with natural units, which is why you have all these factors of c and h bar. If you had these presented to you in natural units, they look a little different, but it's the same thing, so there's really just a choice of preference there. So we'll start with a fairly famous equation, the mass shell equation, mass shell relation. You may have seen it presented a different way. I chose to put the c squared down here below the e squared, but again, it's the same equation. And we can notice that on the left side here, we have the square of the form momentum. Now the form momentum is just E over c, and then the spatial momentum. So if we take this with the dual, which just picks up a negative here, we get that this is equal to negative e squared over c squared plus the spatial momentum squared, which is exactly what we have over here, just negative. And if we rearrange some things, we get negative this invariant equals m squared c squared. If we move it over, we get that this invariant plus m squared c squared is going to be 0. Now, let's construct this form momentum in terms that should be familiar. If we let this equal I h bar times the derivative, this mirrors the quantum mechanical version of the momentum operator, which is just I h bar del. If we plug that in here, we get negative h bar squared d mu plus m squared c squared equals 0. And these derivative operators need something to act on, otherwise this doesn't tell us anything. So because this whole thing is 0, we can have them act on anything. So let's have them act on a field. Now, dividing by this negative h bar squared, we get the form d mu phi minus mc over h bar squared phi is all equal to 0. And that is exactly the Klein-Gordon equation. So the Klein-Gordon equation is just telling us that motion has to satisfy the mass shell relation that we're all familiar with. Now let's move on to how we actually get the Lagrangian from this. So, as you know, Lagrangian is written in terms of the generalized variables as so. And from this we get the Euler-Lagrange equations, which tell us the equations of motion derived from this Lagrangian. For us, we're going to let these generalized coordinates be as so. Now, it just takes the form that is more applicable to our case with fields. That is what is really nice about being able to work with generalized coordinates, is that they really are general. We don't have to just generalize to say rotational velocity instead of translational velocity. We can generalize them. Now, from here, I'm going to get a little messy. So if you're very mathematically inclined, you are a big fan of pure maths, you might want to plug your ears for a minute, because what I'm doing is in no means a rigorous derivation. But I just want to show how can we work backwards knowing that the Euler-Lagrange equations for the free Lagrangian got us this equation of motion. So first, let's start with this term. We could either pick up a phi on this term or pick up a phi on that term from the integration. Now, the Lagrangian should be kinetic minus potential. So we should have one term that's just telling us about how things change and one term that is not. So it'd be kind of nonsensical to attach a phi over here. So we're going to say that there was no phi in the original Lagrangian on this left term, and that contribution is going to be 0. So now we just have that this has given us the constant term times the scalar, which means in the original Lagrangian, which I'll begin to write down here, we get negative 1/2, sorry, that's a bad one, mc over h bar squared times phi squared. Now for this term. So we're taking this derivative, acting on what we get from taking the derivative of Lagrangian in respect to that derivative. And if we think about it, that will sort of bring us back to what we had, because it will cancel something out and then we'll bring it back in. There just might be a numerical factor from whatever power. So we know there can't be a numerical factor over here because it can't be any further terms that would give us that. And we know there's not going to be an extra constant term that gets erased by this derivative and never brought back, because these derivatives have to come in pairs. We need to be Lorentz invariant, and so we need to make sure that everything is invariant. So every derivative has to come with its dual. So the only thing that could get affected by this is this first term here, which originally will pull down a factor of 1/2, because you can kind of essentially say that this is squared. So what that will give us is 1/2 exactly what we see up there. And this is negative because of this negative sign here, and these negatives can both cancel, so we get that the final Lagrangian is just equal to 1/2 d mu phi plus 1/2 mc over h bar squared phi squared. Okay, if you're a mathematician, you can unplug your ears now. We're done with the messy integration that was done using a lot of just thinking about it and not a lot of very rigorous math, but that's okay. Now, I want to show something very cool about the Klein-Gordon equation. So if we rewrite one of the other equations, we'll go with the equation for a vector field. So if we write it out, d mu f mu nu minus mc over h bar squared a nu equals 0. Now, f mu nu is just equal to kind of a commutator sort of expression here with these indices. If we plug that in here, we get d mu a nu minus, and I'm actually going to move it closer to the vector here, and you'll see why. d mu a mu minus mc over h bar squared a mu equals 0, a nu. So if we look at this expression here, this first tensor is symmetric, and the second tensor is antisymmetric. And the second tensor is antisymmetric. The only thing that can come from acting a symmetric tensor onto an antisymmetric tensor is 0. So this just reduces to d mu a nu minus mc over h bar squared a nu equals 0, which looks exactly like the form of the Klein-Gordon equation. Because all the Klein-Gordon equation is telling us is that it's a field that satisfies Lorentz invariance and mass-shell relations and all the fundamental physics principles that everything has to satisfy. We haven't imposed any additional conditions because it's spin 0. So of course every other field has to also satisfy that. Now, with having vectors, we're talking about more interesting objects. They have additional transformation conditions. They have all sorts of additional physics that they bring into the field. And so we get additional terms here, and they look a little different because we have more to add. But they always are solutions to the Klein-Gordon equation. I hope you enjoyed, and I hope you join me for more big concepts.